Brad?
It's never a good thing when just trying to run a PowerPoint slide and you get to the waiting arrow, the waiting arrow. Computer's
got
struggling
things on its
sometimes.
mind.
Yeah. All right. Well, while we are waiting on other people and as we're getting started here. Morning. Let's, come on, you can do it. You can do that. We seem to be a little stuck at the moment. Oh.
I would have been outside, but Sarah stole my parking spot.
That happens.
It's too slow.
Those prime spots, you know, they go fast. We are having some problems here. So first off, how did acid-base extractions and everything go in lab? That kind of helped. I don't know, shed light is the right word, but help you process the idea that pH can affect solubility. It's still going to take some practice before you can get to where you can consistently and intuitively look at a molecule and know whether it's going to be more soluble at high pH or low pH. But we'll get there. Maybe we'll just see about presenting from here. Can I do that? Perhaps not. All right, hang on. We'll try this one more time. Slide 4, apparently. He's giving it trouble. He really does not want to advance to slide 4. There we go. Okay, so if we have pentanoic acid in water, let's practice by writing out what the ionization reaction would be. And drawing the structures of the conjugate acid and conjugate base. And then once we have that reaction drawn, we'll talk about pKa again. Fred?
Is it still considered ionization if it means one is charge?
Correct. It's ionization because it's, now I have to think about this. Whether I can say it like this, the water is being ionized either way, right? This molecule is as well, but I think it's from the point of view of the water. The water is becoming an ion one way or the other. So, and to further clear up that question a little bit, from the point of view of the organic molecules, at least the way that I usually speak, I'm usually going to talk about the organic molecules, not in ionized versus deionized form, but in protonated or deprotonated. That's the way that makes the most sense to me, regardless of what the functional group is. We'll talk about, does it have the proton or not. But the ionization reaction of a weak acid or a weak base is still really common language, so I want you to have seen that. All right, so we've got an acid group, we've got something that can give up an H+. Remember, a hydrogen attached to an oxygen is always going to be easier to pull off than a hydrogen attached to pretty much anything else, barring any resonance that could happen. Especially if it's an acid group, where you've got this carbon-oxygen double bond attached to an OH group, because the deprotonated form has two stable resonance structures. And so we're deprotonating the acid. So if our solution has a pH of 3.5 and the pKa of this acid is 4.8, is more of the acid ionized or protonated? Protonated. Because at a pH of 4.8, we have an equal amount of these. If we increase the pH, so this is another way of thinking about it from Le Chatelier's principle. If you look at this as an equilibrium reaction, increasing the pH is adding product, right? We're adding H3O+. Sorry, decreasing the pH. Decreasing the pH is adding H3O+, which is going to make equilibrium shift to the left. Right? In other words, is it better if we started with 50-50, you add a bunch more of this, is a better chance that one of these runs into one of these to make the protonated form. Right, so there's a whole lot of ways you can think about this logically, and they should be internally consistent with each other. If you like thinking about it just from the mathematical point of view, you can always just come back to this. Right, if your pH is less than pKa, that means this whole term must be less than 0, which means this fraction has to be less than 1. In other words, the bottom has to be bigger than the top. When I was a student taking OChem for the first time, I preferred this because it seemed cleaner to me, and I was still wrapping my head around this. Now this makes more sense to me, now that I've gone to grad school and then spent several years teaching it. So I don't know what will work best and what makes the most sense for you all, but there are multiple ways to look at it. Let's look at benzoic acid again, and then talk about solubility. If the solution has a pH of 6.5 and the pKa of benzoic acid is 4.2, will the molecule be more soluble in water or a nonpolar solvent? Same type of question, I'm just not asking you the leading parts all the way through it, right?
It would be water because the ionized form is more prevalent, the conjugate base is.
Yeah, so, exactly.
And it would be polar, so water.
So because we would be starting, our choices are the protonated form, which is neutral, or the deprotonated form, which has a charge. If we are talking about, we we want to know which of these two forms is going to be more prevalent, because that's going to tell us which solvent it's going to dissolve in. If the pH is 6.5, we don't have very much H3O plus around. We've taken away H3O plus from when it was balanced, when these two were 50-50. So if we're missing H3O plus, equilibrium shifts this way. Or the other way of thinking about it is, if your pH is higher than your pKa, you have more hydroxide around than normal. And hydroxide is likely to bump in here and steal a proton, as opposed to being more acidic, where you have extra H3O plus, and something is more likely to come around and donate a proton. Right, so we have more of the deprotonated form, the benzoate, prevalent, because our pH is greater than our pKa, which means it's the charged form that's more likely. Charged form versus the neutral form, the charged form is going to be more soluble in water. Right, and just because it seems weird, I'll reiterate on the language one more time. It's more of the acid ionized or protonated. Seems like those both have D versions, right? There's deionized and deprotonated. Why would I mix and match these two? Well, because deionized is the way we talk about water, not the way we talk about molecules typically. I could say protonated or deprotonated, but I wanted you thinking about the fact that one form has a charge and the other form doesn't. And so protonated and deprotonated is a more common way of describing things, because then you don't have to use deionized to mean a molecule, because that's a really weird way of using that word. It's not technically wrong, but you would get some odd looks if you were in a group of chemists and you said that the molecule was deionized. And probably at this point in your chemistry education, it should sound weird to you to say a molecule is deionized, because that's how we talk about water. All right, I gave you two examples that are both acids. What about something that has a nitrogen group instead of oxygen groups? So, for instance, we had methylamine. Plus water. That will still go through an ionization reaction.
I just want to be clear on the last one. It would be more soluble in water.
Correct. And if you want benzoic acid to be more soluble in the non-polar solvent, you need to drop the pH below the pKa. If we've got an amine plus water, the amine's not going to act as an acid, right? It acts as a base instead. So we actually wind up with the protonated form on this side, on the product side here. So if, let's say that pKa, and really we'd be talking about the pKa for this molecule now, acting as a weak acid. Let's say pKa is 9.8. What is it going to be? And let's still use the, say the pH of the solution is 6.5. Is more of it soluble in water or non-polar solvent? So this is our pKa, non-polar, yeah. This is our pKa. This is where we have equal amounts of these, right? If our pH is lower than that, we're more acidic, which means we're more likely to have the protonated form, which is the charged form. So
More and more.
still more in water. I know I said yes to you, Miranda, but so both of them at a pH of 6.5, both of those molecules are more soluble in water. Because both of those functional groups are likely to be present in their charged form. But one of them in its deprotonated form is charged and one in its protonated form is charged. The other way that I've presented this before is to treat it like pH like it's a number line. You think of pH as being a number line where you've got 7 for neutral right in the middle. If you come in and you drop a line at pKa, so pKa for, let's go back to benzoic acid since the numbers are on the slide there. There's our pKa. Anything to this side of that is going to be missing, is going to be the deprotonated form, right? It's more basic. Anything this side is going to be, so we can say acidic over here, so therefore protonated. Basic on this side, therefore deprotonated. Right, and so pKa can slide back and forth, but the acidic, basic, protonated, deprotonated doesn't change. Just which form is charged changes depending on the functional group. And where pKa is depends on the functional group. So for an acid, we could then come in here and say deprotonated is charged versus neutral. Right, so again, one more way of visualizing this and realizing it's not really a binary state. It's really a mixture of everything as we go, but this is our really handy dividing line at pKa. All right, so questions about pH and pKa for right now. Hopefully by this point you guys have had enough experience with weak acids from last year that it makes sense on a fundamental level, even if you can still get lost of walking your way through the different steps. But each of the steps individually should make sense. It's like those big long conversion word problems you used to have to do, right? Where each of the individual steps was easy enough, but stringing them all together without making a mistake was really hard. Same thing here. Each of the individual logic steps is pretty straightforward, but getting all the way from here's your pH and your pKa, where's it soluble, takes a little bit of work, a little bit of practice. I was telling my Gen Chem students they have their first set of word problems in Gen Chem right now. And so I told them that they could talk to any of my OChem students and ask them if they remembered the black hole problem, and that you would pretty much all say yes across the board. Maybe not how to do it, but you remembered that it was there. And they told me that wasn't a good thing. I told them I disagree. All right. We've laid some groundwork when it comes to orbitals and pH and pKa so that we can understand some physical properties here. Now we're going to get into stuff that a lot of times gets covered. The very first thing you run into when you walk into an OChem classroom is here's an alkane, here's how you name it, and memorize this. I like to lay a little groundwork and background first so that what we're going to talk about in the future makes sense. But this is stuff that almost certainly you saw last year at the end of Gen Chem. If you, I think everybody who took Gen Chem, right? I don't think I want to put anybody that skipped Gen Chem. So this should mostly be review. So we'll knock out some vocabulary, and then start practicing with organic nomenclature, get you back in the swing of that. First off, hydrocarbons is a term that gets used a lot. We're pretty quickly going to leave that behind in organic chemistry because we're going to get more specific than that. So hydrocarbon is really, really generic term. It just means literally any molecule that's only hydrogen and carbon. So that's a pretty narrow subset of molecules, but still not enough to describe it because it still leaves out that you can have a lot of different functional groups that are considered hydrocarbons, but they're going to react very, very differently from each other. So, at their most basic, you can have everything in sigma bonds, everything in single bonds, which is what we call an alkane. And an alkane is defined as a hydrocarbon that contains no pi bonds, which when we walk that backwards means you have only sigma bonds, right? And only carbons and hydrogens. Is our definition of an alkane. As you start adding pi bonds, things start getting more complicated. You can have an alkene, an alkyne, you can have aromatic molecules, and we'll talk about all those as we start adding functional groups and reactions in a little bit. But these would all be considered hydrocarbons because they all have nothing but hydrogen and carbon. But before we can really get the hang of naming those, we're going to practice until your eyes go crossed naming alkanes and trying to find all the complicated ways I can give you a simple alkane that can try and trip you up on the nomenclature thing. Because if we get that down, all the rest of the organic nomenclature is just adding wrinkles to the same basic rules we use for alkanes. All right, so compounds used to be named randomly as depending on who discovered them, which led to some really fun names, some really historically significant names, but it's really a pain if you want to actually try and know from the name what the structure is. It was basically memorizing. So for instance, formic acid. Formic acid is a one carbon carboxylic acid. And it's actually named because it was first isolated from ants, and formica is the Latin term for ant. So formic acid, if you've ever smelled, I don't know, I remember being a kid and being tasked with getting rid of an anthill on the driveway, and being a kid and not being a chemist at the time, my first thought was, I'm going to get a big rock and I'm going to squish all these ants at the same time. And you get this really, really sickly sweet smell. Has anybody ever been squishing ants and you just smell that? That's formic acid.
You do the magnifying glass.
Yeah, I didn't go that route. They run away from that too fast. But yeah, so you can actually smell that. It's acidic, but it's also sort of sweet. So not like vinegar. Vinegar is acetic acid, which is 2 carbons. Urea was named because it was isolated from urine. Easy enough, right? That's the compound that you get from urine, therefore urea. Morphine was named after the Greek god of dreams, Morpheus. Kind of paints the matrix in a new light when you know that Morpheus is the Greek god of dreams. Changes some symbolism maybe in there. And then you've got barbituric acid, which is named by Adolf von Baeyer. That's the same Bayer for Bayer aspirin. Bayer aspirin, he's the man who first synthesized and isolated aspirin and marketed it as an over-the-counter painkiller. It was competing with things like morphine at the time, so it was not always a great seller when you have this as an option. But he just named it after a woman named Barbara, which was not his wife. I'm not sure we know who Barbara was, but it was not his wife. So it seems like that's just asking for trouble, right? You had the option to name it after your wife, and you decided to name it after some other woman. So fun historical notes. Adolf von Baeyer was not a very pleasant man in general. He's one of the primary reasons why the German military was able to be built back up the way it was post World War I. Prior to World War II, and he wasn't, mainly because he was on the economic side, but he was lobbying very, very hard and buying into a lot of the propaganda that Germans were being unduly persecuted after World War I. and which eventually led to the Nazi Party taking control. At that point, he was already very, very rich, and he was just sort of, you know, spitting vitriol just because he was angry. So now we use systematic names, so we don't have to remember what morphine looks like based on its name. Although that is one of many compounds where the common name is still the easiest way to describe it, because the systematic name for a molecule as complicated as morphine winds up taking up 3 lines of single space type. So a lot of times we still will use common names for a lot of things, but systematic names are the way we can have that are unambiguously get you to the right structure every time. And so they're always going to be named according to the longest continuous carbon chain and the functional groups. Right? And so the longest continuous carbon chain is easy to define when we're talking about alkanes, and we'll start adding wrinkles to it as we go and add functional groups. But it's generally, you're going to want to pick the longest continuous carbon chain that has everything attached to it. For alkanes, there is nothing specifically that that is more important. There's no one chain that's more important than others because there are no extra functional groups. Everything is an alkane, and an alkane is our sort of our baseline against which everything else is compared. So alkane is the lowest priority functional group. So all we're worried about with alkanes is what's the longest continuous carbon chain. And a lot of times we call that the parent chain or the parent molecule or the parent compound. Just means that the one that you're going to name it based on the parent compound, and then you're going to modify it by using prefixes. Right? Think of all the prefixes that we're going to add are just going to be modifying the parent compound. Right? So the longest continuous carbon chain is not always going to be written left to right. It frequently is. If you're starting from the name and drawing something, it's usually easiest to start by just saying, oh, it says hexane, I better draw 6 carbons in a row. And it's usually convenient to draw that as a straight line. But if you're starting from a structure, they're not always going to be drawn in a way that makes it so that the parent chain is left to right or one continuous straight line. It's just going to be any way that you can count to the highest number without doubling up on carbons. So you go 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, we're looking for the longest continuous carbon chain, which would be going around this way. All right, so, and you don't have to start on the left-hand side. You can start wherever you need to make it the longest continuous carbon chain. You could start at the bottom and count up. You could start at the bottom right and count up. You could count, wherever you need to. You can go in a big circle. As long as you're getting your longest continuous carbon chain. And then once you have that parent chain, especially if you outline it in red like this, it becomes obvious that you just have a few extra things hanging off of that. So each of those extra branches that we have hanging off of that, we're just going to name with a prefix. So the base names, we actually use slightly different names for the number of carbons than you would think based on Greek or Latin. Probably because they're trying to avoid confusion. They wanted a different set of prefixes, numerical prefixes, so that you didn't wind up with things like monomone. So we actually have especially down 1 through 4. From there, that's pretty standard Greek prefixes. But for 1 through 4, we use different prefixes. Meth means 1, F means 2, prop means 3, but means 4. what I always see, and you guys have seen this before, and you guys have practiced this enough, I'm sure that none of you would make this mistake. But what I always see is that, and I think that the tendency is because F has fewer letters to make F one that means one. That's not how it works. A methyl group is one carbon. The other one that trips people up, people don't typically mix up like meth and prop. They mix up meth and F and prop and bute. The way that I keep these straight is propane is a gas, butane is a liquid, therefore butane is bigger. Right? So once you get it down, you don't have to think like that, but I think everybody has enough experience with propane grills and a butane lighter to know that butane's a liquid, propane's a gas. Right? So therefore butane must be bigger than propane. Right?
Are you hinting at that we need to then memorize these?
Yes.
Okay.
And it's one of those things that it won't take long because we're going to be using them so consistently. I only ever see those mistakes made the first quiz, basically, after we cover this, because after this, we're going to keep using it and using it and using it and using it to the point where it will be second nature very quickly. So, if we start from a molecular formula, and we want to draw the complete structure of the alkane with this formula, C3H8. Give that a go, draw the complete structure. Let me know if you find any constitutional isomers. I like your shirt. I just thought it was a Pink Floyd shirt when you walked in.
Yeah, it's tricky like that. Or you might say it's stolen intellectual property.
Some might say that. And others might say that stolen intellectual property is an oxymoron. Any constitutional isomers? Any way we could rearrange these differently that gives us a different molecule? Now, we could change the way it looks, but if we just switch this hydrogen and this carbon like we talked about, it's still 3 carbons in a row, right? So that's just another way of twisting around the same molecule. So our longest continuous carbon chain is 3 carbons. Can't be any longer than that because we only have 3 carbons. It can't be any shorter than that because there's no way to rearrange these so that it's not 3 carbons in a row. So if we wanted to name this, we identify our longest continuous carbon chain, then we use prop as our base. Prop meaning 3, and because it's an alkane, we just add ane to the end. So propane. Right, so, Brad?
So, this 3?
Yes, you weren't here the other day when
No, I wasn't. And I read online that this is how you start, and I still did it wrong, but I think
That's okay.
molecules were a little bit more complex.
No, actually, it was physics that I think I wandered into, and I saw Sarah and Rigney and told them that quiz was not supposed to be open yet because we hadn't covered the stuff yet. When I switched over the dates during the evacuation and our quarter being postponed, I missed that one. So you should never have to do 2 quizzes on the same weekend. So always just go with the lowest number if that happens again. And I just went through and I gave you another try on it. So I'm just going to ignore the first one.
Thank you.
Yeah, no worries. Sorry about the confusion. If it's C4H10, adding one more carbon and two more hydrogens, right? So the simplest way to draw it would just be 4 carbons in a row. That adds 2 more hydrogens. You can actually think of it as splitting this open and sticking one CH2 right in the middle. Right, which is why we go up by 1 carbon and 2 hydrogens. So now our longest continuous carbon chain is not 3, it's 4. So it's not propane, it's butane. Right, so all you're doing with these prefixes, or with these base names, is you're indicating what's your longest continuous carbon chain. Right, and then aim, the ending of the molecule, is always going to say what's the most important functional group we have attached to it. If there is no functional group attached to it, then it's an alkane. If we had an alcohol attached to it, we would modify this aim to be something else. But we would still start by finding the longest continuous carbon chain and using this base. Problem with C4H10 is that there are constitutional isomers now, right? So butane would be 4 of them in a row. But what if we put one of the carbons off to the side? Now all of a sudden it's not, our longest continuous carbon chain is not 4 carbons. We've got a total of 4 carbons, but the longest continuous carbon chain is only 3. No matter which way we count, we get the same thing though. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. No matter how you do it, you get 3 in a row with 1 extra carbon hanging off the side. So our base molecule, our parent molecule, is still going to be propane because it's still 3 in a row. And then we're going to say we have an extra carbon by adding a prefix to that. Right, so here's the 3D structures of butane, and sometimes you see this called isobutane, but that's a common name. That's an old school way of naming it. We're not going to use that too often. Butane, and this is a propane with an extra carbon. You want to practice drawing the condensed structure for these. The condensed structure for butane is really easy, right? CH3, CH2, CH2, CH3. The condensed structure for the propane base would be CH3, CH, in parentheses, CH3, CH3, or sometimes you'll see these combined and put CH3 with a 2. I think this way describes more in just 2 extra characters. Describes what's happening more, so I prefer this way. But you certainly might see it as CH3, CH, CH2, or CH3, 2. I don't prefer that though. It doesn't even save you that much room. And especially if you're typing in Word these days, you have your keyboard shortcuts for subscripts and superscripts. You still have to go subscript 3, back to regular for the parentheses, then back to subscript for 2. More keystrokes, frankly, than just laying it out like this. I guess it's the same, but point remains, this looks better.
Sean, when you took butane and then you morphed it into a constitutional isomer, then what was the name of that? I missed that part.
We haven't done that yet.
Oh, okay.
So I'm making the point that there are 2 different molecules that are going to have different properties,
Gotcha.
different condensed structures, therefore they have to have different names. Right, so because the rule, this is what I want to drill home with this, is from the name, you should always be able to get to the exact structure unambiguously. There should be no choice. That's why we don't use molecular formulas that often. Because from a molecular formula, you're limited to, well, all of these are constitutional isomers, how do I pick? from the name, you should be able to unambiguously get to the exact structure. Sarah?
I was asking like what the keyboard short against for subscript.
So on Word, it's Control equals gives you a subscript, and Control Shift equals gives you a superscript. I don't know what the one is for strike through. I have all the rest of them memorized. Underlines, Control U, Control B is bold, Control I is italicized. But I don't know strike throughs. So if we have constitutional isomers, and our name must be unambiguous, we need different names for these two. So if we're naming this what we refer to as a branched alkane, as opposed to a straight chain alkane, a branched alkane, we still find the longest continuous carbon chain, and then get the appropriate base for it. So for this molecule here, it would be 5 in a row. So we start with the base pent for 5. There's no other functional groups. We add the ane. We name that parent molecule just like normal. So 5 carbons in a row, we can name that pentane. And then the prefix that we're going to add is supposed to indicate the size of the branch, or the size of the side chain. And so you use the same bases for numbering the size of the side chain. You just add YL, turn it into a prefix. All right, so for our molecule over here, our base name would still be propane, because our longest continuous carbon chain is still 3. We have a single carbon hanging off of it. And meth means 1 carbon, and then to indicate that it's a branch, you add that YL, methylpropane. This one would be methylpentane. The problem with stopping there is that for as you get to larger molecules, is methylpentane an unambiguous name? Why not, Rigney?
Because that methyl group could be anywhere on the, anywhere on those 3 carbons.
Right, we have to specify where the methyl group is so that we don't mix up our methylpentanes. We don't have to specify it here, right? Because there's only one place we could put a methyl group on propane. If we try to put a methyl group there on propane, we didn't add a branch, we just made the main carbon chain longer, right? So that just takes it to being butane. So for methylpropane, we don't need to specify where the methyl group is because it can only be in one place. But the second that we get to larger molecules, we have to specify where the methyl group is. And we do that really easy way by just adding a number in front of the prefix. So we would name this molecule would be 3-methylpentane. Methyl tells you have a 1 carbon branch. 3 tells you it's on carbon 3.
And you want that number to be the lowest possible, right? So it would be like depending what carbon it was on, like if it was on the one to the left or right, it would still be 2-methylpentane because you would count from whatever carbon makes that number the smallest.
So if we had the methyl group in a different place, this one, intuitively, you would say 2-methylpentane. But remembering that these are 3-dimensional molecules, this is also 2-methylpentane. The same reason that you don't just count from left to right when you're looking for your longest continuous carbon chain, you don't just count from left to right when you're trying to find the number. You find the lowest possible number. This is not 4-methylpentane because it's just 2-methylpentane that you flipped over. So you always count from the side that keeps your numbers as low as possible, which takes a little getting used to. If you said 4-methylpentane, it's still going to give you the same molecule if you try to draw that, but it's a little redundant because these are not two different molecules. So we wouldn't actually say that. And if you did miscount and count from the wrong side, it's one of those things like I was saying earlier that if you said 4-methylpentane in a group of organic chemists, they're going to know what you're talking about, but they're going to look at you funny.
So you're just saying it's mundane because you could just split, right?
Exactly. We don't want to have two names for the same compound if we can avoid that. We have enough of that already when it comes to common names. All right, so we're always going to count from the side that keeps numbers lowest. And when it comes to how to write these, the Iupac is I'm going to butcher the name, the International Union of Practical and Applied Chemists. This Iupac is the governing body for all chemists worldwide. They're the ones who just make all the decisions about names. So we call this the Iupac name because it's the one that everybody can agree on is this is the best way to name things. The Iupac name actually doesn't have a hyphen here. It has a hyphen before between the number and the prefix, but then it actually just slams these together. It doesn't even put a space. Which I don't prefer because it's easy to, it's harder on the eyes to see a big, long, especially when you get to larger molecules. I don't like to see it one giant word where I have to go through and intentionally parse out where the prefixes start and stop. So I prefer to just put a hyphen between everything, just for the sake of making it easier to type and uniform and easier to read. But you should be aware that when you're reading, even in our textbook, you will see it all as one word. I just break it up with the hyphens, make things easier on ourselves.
Right?
Right?
It'll always be a, whatever it is after.
If it's an alkane branch. There are other branches out there. For instance, if you had, so whatever the most important functional group is going to always be named at the end of the molecule. But if you can have multiple functional groups on the same molecule, so this would be pentanoic acid, longest carbon chain is 5 carbons. If I put an OH over here, I can't name it as an alcohol because the acid is more important, it's a higher priority functional group. So pentanoic acid would still be the base name, and we would name this with a prefix. This is not a YL prefix. Hydroxy is the prefix. So this one would be 2-hydroxypentanoic acid. So it's not always, but as long as it's an alkane, it will always end in YL. You know me, you can't ask questions that has to say an always statement, right?
Yeah.
Only a Sith deals in absolutes.
I am wearing the hood today.
How did that game turn out the other day? The Chargers Raiders who won. Oh, was it? Sorry. It's not meaning to pour salt in a wound. I just only saw the first score.
I was just funny. I was talking to my girlfriend about it. I was like, I kind of want them to just get it out of their system now. It's very rare a team goes undefeated, and even if they were, that's so much pressure every game. I can't handle that.
Tom Brady couldn't even handle that.
No.
He wound up choking in the Super Bowl,
It
right?
was fantastic.
That was fantastic. All right. So let's name these. It's a lot of times it's actually harder when you see the three-dimensional structures than the skeletal structures, but it's still good practice for trying to find out your longest continuous carbon chain and then what's your branch? You can still go through and circle it in the same way, or you take this and turn it into skeletal structure. Right, so this one we already did, right? It's not entirely obvious when you first look at it, but it's 3 carbons in a row with 1 carbon hanging off, right? So that's our methylpropane. What is this one?
2-methylpentane.
Yeah, 1, 2, 3 versus 1, 2, 3, 4, 5. So pent is longest. So pentane is our parent molecule with 1 carbon hanging off of it. So that's a methyl group. So it's going to be methylpentane. And then we specify where that methyl group is. So the order that I would approach these in, the way that I name compounds, is to get your parent molecule and start adding prefixes. So you're kind of working from right to left on your name. Give yourself a bunch of space to the left and start by writing pentane, and then come back and fill in your prefixes. Don't try to do it left to right, because you're just going to wind up missing things or counting things wrong. Right? Block it up in big chunks. Okay, now I know it's pentane. Now all I have to do, especially if you have it drawn on your piece of paper, once you circle this, all you have to do is add 1 prefix for anything that sticks out of your circle. Right, so methylpentane, and then once we realize, oh wait, we need to specify where that is, you add your it's called the locant. And I don't know if that's a linguistics term or a chemistry term or a chemistry of linguistics term or linguistics of chemistry term. I've only ever seen it with respect to the number that goes in front of a prefix. It's known as the locant, because it tells you where it's located. And how about this molecule here? It's our longest continuous carbon chain. Yeah, it's still going to be pentane. Except now our branch, so if we circle this, our branch is 2 carbons long. So 2 is ethyl. Ethyl is not just a little old lady. Ethyl is a 2 carbon branch. Do we need a locant for that one? 3. It's on carbon 3. It's a little bit redundant actually in this case, because could you have 2 ethyl? What would 2 ethyl pentane look like? So pentane, 1, 2, 3, 4, 5. Add an ethyl group on carbon 2. That's not pentane anymore, right? So by adding an ethyl group on carbon 2, we actually just made our carbon chain longer. So really this is 3-methylhexane. Not 2-ethyl pentane. Again, if you add the 3, as long as you count your longest continuous carbon chain properly, you'll get the parent compound right. And then you can put your prefixes on there based on that. If you add the locant when it's unnecessary, that's a better safe than sorry situation. Right? When in doubt, it's better to have that there. It's just a little redundant. All right. We will continue doing this at 5 after, and we'll start making things more complicated. That's what we do in chemistry, right? Wait for you to get comfortable, and then we make it trickier.
Make sure I drew this one right to the bottom one.
Yeah.
So, John,
Yeah, you said that. Hey,
You certainly could, it would still give you 3-ethyl pentane, wouldn't it?
I read the news on
Yes,
France,
it
and
And that's exactly why,
I feel bad now.
it doesn't matter which way we
I
count.
discussed it, I apologize, 'cause
No, you did not
She would
discuss.
slug me had I told that.
It's,
And you have one about Ethel. Or a woman Ethel, she's in church. And, yeah. She's ready to go up.
Sorry, I feel bad for missing on Tuesday. I'm bummed about it.
No worries, were you able to, did you try the recording?
No, I was gonna do that over the weekend.
Okay,
Because, well, I tutor pretty much right after every class.
yeah,
I don't really have time. By the time I do get done with school, it's 7, or it's like 8 or 9 o'clock, and I haven't eaten usually, and I'm dead by that time.
yeah, no, I agree.
Weekend projects.
My Tuesdays and Thursdays especially, I go 8 a.m. when I start with you folks, all the way through. My office hours don't end until 4. And so I go 8 to 4 with no breaks, and at the end of that, I just can't even see straight. So I feel you.
What time, you're gonna be in at 3 today? 3 hours?
Yes. Yeah, I finish up Gen Chem lecture at 3. So it might be more like 3:15 by the time I get my stuff packed up and finish talking to people up there. But yeah, I'll make it down here. I think I'm actually on Thursdays, I'm gonna actually extend my office hours to 4:30 instead of just 3 to 4 too, so that works better. Because I've gotta get my daughter to dance class at 4:15 at the Y. I have to pick her up at Bijou on one side of town and get her all the way to the Y by 4:15. So I think Tuesdays I'm gonna cut shorter. So Thursdays I'll have a little bit more time. But as long as, you know, if the stuff we were talking about, you might have been a little bit lost with some of the language and the way I was describing things, but if those review things we were talking about at the beginning made sense to you, then most of lecture should be okay. It's a lot of talking about hybridization and then getting into acids and bases.
I've been reading the book, so hopefully what I do find lost to lecture.
This textbook is one where I don't think I have not found a need to go significantly outside of the order that they give you the topics in the textbook. So if you're following along in the book, you should be fine. Before, when I was first teaching Gen Chem, there wasn't a good textbook that did orbitals before stoichiometry. And it just makes sense to me if you're starting talking about atomic structure to go right into orbitals and electron configurations in the periodic table, as opposed to here's a reaction, balance it, now this is what stoichiometry is, and then coming back to orbitals later.
Yeah.
So I used to teach that like chapters 1 through 4, and then we're going to jump to 8 and 9, and then we're going to come back and do 5, 6, 7. But I don't think this OChem textbook, we need to do that, and I've since found it better. The OpenStax does it the order that I prefer anyway, so, yeah.
Yeah, it's funny, some of the OpenStax textbooks I like, and some of them, well, the calculus I would not, I have to get it different.
Stuff where you rely on having, where I've noticed OpenStax falls down, where I use other textbooks on top of it, is topics where a lot of practice problems is helpful, because they just don't have very many practice problems at the end of each chapter. And calculus definitely fits into that category.
So I asked Bruce what kind of book I should get, and I'm so thankful I did. I ended up getting this one.
Oh, that one.
This one. Yeah, I love it.
Who is that? What's the author's name?
James Stewart.
Stewart. Yeah, Stewart's calculus. That's the one. It used to have a picture that the integral symbol was, they used the sound hole on a violin as the front, but it was the same base, same color and same symbol on the front. It was just looked like a violin. That's what I took AP Calc from.
Yeah, by the time I hit fourth quarter calc, I was fed up. I was completely fed up, and I just needed something else. And I kind of feel lucky with this one.
Yeah, no, that's a good one. But how did you feel about the OpenStax one? Or for chemistry, I mean.
The chemistry was fine.
Yeah,
I thought it was fine, yeah.
I have not found another textbook that does significantly better than OpenStax to me, but I'm also coming at it as the person who already knows it, so.
Oh, no, I liked it, I still have it too.
Good. It's what most people say, most science majors say the number one textbook that they still come back to after college is their Gen Chem textbook. Because when you need to go back and freshen up on, wait, how does this happen? Or what's, you know, it's always your Calc 1 textbook and your Gen Chem textbook. Because if you're a bio major, you know everything in Bio 101 by heart by the time you get out, but you might not remember how weak acids work.
So you tell me not to throw in my Gen Chem book?
I would not. I would not.
I'm slowly accumulating books that I feel like I'm not gonna use again, so it'd be good to hold on to.
I mean, I do that too. I have a hard time getting rid of books in general, and I wound up. So, but I think I still have my my History 101 book from college that I haven't cracked since I finished that class. But I don't mind anything related to your major though. It's usually worth keeping just in case. I still go back when somebody asks a good question, good OChem question. I actually have advanced OChem textbooks that are the, you know, the upper division equivalent, and where you really dive into some of this stuff. And so I'll still go back to those on occasion to refresh my memory on how things work sometimes in order to answer a question. But that's in my specific field. I don't do that for biology textbooks. I took some upper division biology, but I never go back to those textbooks.
You said you had the teacher's edition.
Yes. Oh, shoot, I didn't bring it.
So at some point, snap some pictures of just the last couple pages.
Send me an email or put it in,
Okay. I'll do that.
or put it in your question this week for the quiz. And then when I'm grading those, I'll remember, because it's sitting right by my desk at home.
Okay.
It's just
It's a
not,
big book, I get it.
it's a binder. I asked for a free version, so they're supposed to give the teachers free versions of the textbooks.
Yeah, I love them.
And that one, they just sent me a big shrink wrapped stack of papers that are 3-hole punched. So it's just a binder,
But it comes with the answers.
but it has all the answers.
Because I'm getting the skills and the practice, but I don't know, I get nothing to compare it to, so it's like.
Yeah, absolutely. Let me know. Remind me, and I'll try to remember on my own, of course, too. But
I know your wife, I know where you live, I got you, buddy. Don't you
Yeah.
worry. What am I doing?
hey, yeah, if you showed up at my front door and said, "Hey, can I borrow that?" Absolutely, would be the answer. So.
That's the beauty of Tano.
Mhm.
Yeah, I thought about getting a partial differential equations textbook, trying to teach myself, but then I thought, you know, it's probably not a good idea to teach myself wrong, but probably what we're gonna have to do.
Yeah, and DiffyQ is tricky.
It is.
I never took DiffyQ in undergrad, but I had a brief introduction. The way that you guys were introduced to OChem at the end of Gen Chem, I got that at the end of third semester of calculus. I didn't realize, I was playing ignorance. I realized it was probably a whole different class, but I got a phone interview. I was waitlisted for grad school. I'm like, your transcript says you haven't had differential equations. Like, oh, no, that's Calc 3 at our school, which was not true, but I didn't know any better. So I got into grad school with a false percentage that way, and then so I jumped right into numerical methods, which is solving differential equations that don't have an analytical solution.
Oh,
So going to the grad school equivalent of the second in a series when I didn't have the first, I don't recommend that. I would rather have just taken differential equations. Yeah, so teaching yourself differential equations can be a little bit tricky.
yeah, I'm sure.
You want to read Beautiful Mind, I think they came out with a
Yeah, Russell Crowe, right?
Crowe as well.
Yeah,
The book talks about, Nash is the characteristic in my mind, but it talks about at some point in his youth where he could do some high-end calculations, but like at a certain age, you could feel it start to deteriorate. It was like right around 28, he started to feel this, but he was also dealing with some mental
Right.
as well.
Well, and that's a common thing among mathematicians is that they say that in mathematics, if you haven't made your mark by the time you hit 25, you're probably not going to. You're just going to be, you might keep doing math research, but you're going to be sort of middle of the road. You're never going to excel.
Yeah.
Whereas other fields, like engineering in particular, you don't start doing your best work till 45, because that's when you've seen like enough of what's out there to really be able to sort of hone in on things. So yeah, mathematics, though, in particular, is known as you either make your mark and burn out early, or nobody will ever know your name. And you won't, you don't win a Fields Prize, which is their equivalent of the Nobel Prize,
Right.
Unless you've done your work by about 25. I don't know why that is, but that's the common trend.
There's always outliers, right?
There's always outliers. You could be an outlier.
And there's something called neuroplasticity, that's what I'm banking on. Neuroplasticity, baby, come on.
Yeah, bring that back, that flexibility. I really do think a big chunk of it too is, especially if you have kids, is sleep deprivation.
Yeah.
And I literally don't think I will ever recover. I was teaching 3/4 time at 2 different schools when my son was born. So I was working about 70, 80 hours a week with a newborn at home. And I legitimately don't think I will literally ever recover from that fully. Like there's only so much you can do to make up for sleep deprivation for 6 months straight.
There was some
Try being the mom and having your body and hormones
Oh.
forever change.
Yeah, no, I can't even imagine. It's just like, I feel like that's a big chunk of it too. I feel dumber than I used to
Oh,
feel.
yeah. It's real. It's a real thing.
There's definitely settlements before education that said get it out of the way before kids. I did that stuff.
She ain't what she used to be, this old brain.
Yeah, I would get home and I was teaching, half of my classes were on the other side of the lake at SNC in the incline, and so I would finish teaching there at 9, drive home, get home around 10, have to grade for half an hour, go to bed at 11, wake up to take care of the kid at 3, go back to bed for an hour, wake up at 4, and start prepping lectures for the day. And it was just like, ugh.
Yeah, you feel like you're going crazy.
Yeah, you really do.
Yeah.
And throw a quick cold in there when I was drinking way too much cough syrup at the same time, and I just really had no fix on what was real and what wasn't.
Oh, yeah.
All right, if we have multiple branches, our rules don't change. We just add multiple prefixes. So in this case, our longest continuous carbon chain, no matter which way you cut it, is still 5. Right? If I put it as skeletal structure and try and keep everything more or less in the same place, it doesn't matter where you start and end, the longest continuous carbon chain you could get is 5. So, with that being the case, might as well just go left to right. So our parent molecule is still pentane. And if we didn't have the ethyl group here, we just name this as 2-methylpentane, right? So we just put both prefixes on at the same time. So it's 2-methyl. And then if we didn't have the methyl, we'd name this as ethyl, right? And when you start getting to multiple prefixes, people are going to be less concerned if you add that redundant 3 in front of it.
So this one was confusing to me because wouldn't it be easier to name it 3-propylpentane and just have that off the 3rd carbon be the branch?
So you only have one branch if you do it that way.
Yeah.
But that branch itself is complicated. the branch has a branch. You can't just name it propyl, because propyl would be 3 carbons in a row as a branch.
Yeah.
So there's a common way to name this sort of group called an isopropyl group, where iso is like isosceles, means the same. It's 3 carbons, but it's the same either direction. That's not the Iupac way to do it anymore. So the way you would name it this way is if you have a branch within a branch, use parentheses, like you do in math. So this would still be pentane. And now the longest continuous carbon chain that starts off of the main chain is 1, 2. So we would say, okay, this is an ethyl group attached, but then the ethyl group has a methyl on it. So we would name this as I didn't leave myself enough room. A methyl-ethyl group. And to indicate that this methyl is applying to that ethyl and not to the pentane, we put it in parentheses. So the parentheses just mean that this methyl gets applied here, not there. So it's a lot like math, the way that the parentheses are saying, do this first. For the parentheses here are saying, apply this prefix here first. And then we could say, so yeah, we could say it's 3 methyl-ethyl pentane. That's not wrong. Typically, and learning how to use these prefixes or these parentheses is really helpful. The temptation is to use the common name and just say isopropyl when you run into something like this. I would encourage you to learn how to use the parentheses when we do this, because when you get to branches that are longer than just an isopropyl group, it gets really, really tricky. So for instance, if our longest continuous carbon chain was a 6-carbon ring, how do you name that? Well, if you know how to use the parentheses, this is the same, more the same. This is 1, 2, 3 carbons, so it's propyl that has a methyl on it. So this would be a methyl-propyl group. But if you try to use the common names like iso, this is actually, is it a sec-butyl group, I think? It's less systematic and less easy to apply to new situations compared to if you learn these. But what's generally easier than even using the parentheses is a lot of times just by picking which way you count. If you have multiple choices for your longest continuous carbon chain, count the way that makes it so that you don't have any complicated branches. Right, so it's only 1 branch if you do it that way, but that branch is complicated versus the way we started, it's 2 branches, but each of those branches is easy. And typically, I believe that this is going to be the more common name as well. And you will see this used more. These are technically both correct, but avoiding complicated branches is the rule of thumb.
And do we do higher branch first?
So, Iupac rules will generally say that you're supposed to alphabetize. So ethyl comes before methyl because it's an E before an M. But then there's disagreements as to what happens when you add di in front of one of these. If it's dimethyl, do you alphabetize that according to D or M? Different textbooks do it differently. So I'm not going to be picky on the alphabetization. As long as you get all the prefixes there with the right locants, it doesn't really matter what order you list them in. I will draw the same molecule anyway, right? And that's what we're really looking for.
So at that point, it's just semantics.
At that point, it's just semantics. I will still try to put it in the autograder on Canvas alphabetically. But if you put them in a different order and get marked 0, I'm going to go back and give you full credit when I do the grading.
Do you use yourself one way or the other, the by, try?
I kind of go,
Or you go off the base word as the
Typically what I actually do is when I find my parent molecule, I just then I start at one end of it and start adding prefixes. In this case, it happened to be the methyl first and then the ethyl.
Yeah.
And so I just sort of build it based on the way the structure is drawn, but I don't have a preference really one way or the other.
Okay.
If I happen to think about it, I would put them alphabetically, but really I'm just going from right to left and writing it out. All right, and just to reiterate, I already mentioned this, but just so we see it, if you have two branches that are the same length, you use our standard Greek prefixes for how many of that branch you have. So the organic base name tells you how big the branch is. Di, tri, tetra tells you how many of them you have. And we never use mono to indicate one. Just if you don't put a prefix, it's assumed you mean one methyl group. So the trickiest thing that people get hung up on with that is not forgetting to put di or tri. It's that forgetting that means that you need a locant for each of those branches now. So here we've got our longest continuous